Okay, this video is just to try and allow you to become a little better acquainted with reaction mechanisms and how we represent them using these curly arrows here. So as we said before, right, the curly arrow shows a movement of a pair of electrons. So it's two electrons. And if you think, we know that electrons in their orbitals, they're always, except in the case of free radical, and they're very reactive, they're always paired up. So you can either have a bonding pair, can't you? Or you can have a lone pair. That's why in these diagrams you always show the arrow starts from either a bond or from a lone pair and moves somewhere else. Yeah. Okay, so I thought we'd look at a couple of reactions, some of them familiar, some not familiar, and how we'd represent them using curly arrows. So let's think about when you get ammonia gas, NH3, okay, and it's very soluble in water, and it reacts with water to form. So the ammonia takes a proton off the water, and it becomes NH4 plus, and it leaves behind OH minus. Okay, and I should really change that into an equilibrium arrow because most of the ammonia, when you dissolve in water, just stays as dissolved NH3. It doesn't actually gain the proton. But okay, so let's see what happens there. So I'm going to draw. Sorry, need me to do that. Let's draw ammonia. So there's our ammonia. Let's draw water in black. Now ammonia, the nitrogen has got a lone pair in it. It's got a lone pair, and that's a pretty strong lone pair, a pretty strong negative charge there because the nitrogen is an electronegative atom. And nitrogen is a pretty good base, and ammonia is a pretty good base. What's going to happen is that pair of electrons is going to move off and form a covalent one. So the lone pair is going to stretch out and form a bonding pair instead to that hydrogen. And that hydrogen would then be forming two bonds, wouldn't it? And so one of the bonds has got to, the other bond's got to break. So what happens is the pair of electrons in this, go back onto the oxygen. So essentially, the pair of electrons in that bond there, they stop being a bonding pair and they start being a lone pair. All right, so what would that look like? It would look like we'd have NH, not just 3 electrons, but we've got this, it's not 3 electrons, 3 protons, we've got this hydrogens, we've got that one there from the water, so the whole thing has got a positive charge, and well, the water, it's not water anymore, it's OH, and that's OH minus because it's got 1 electron. It shouldn't have. Right, let's show it going the other way now. So let's do it going backwards. What would happen there is, well, let's say the oxygen is going to get back its it's going to get back that H plus. So this lone pair is going to stretch out and form a bonding pair to the hydrogen. No longer a lone pair, it's a bonding pair. And of course, then that means that hydrogen can't have this bond anymore, can it? So what's going to happen there? Well, the pair of electrons in that bond are going to shrink back and become a lone pair again. So instead of being a bonding pair, going to be a lone pair, and that will, you're going to form the NH3 and the H2O again. So when you dissolve ammonia in water, it's constantly going backwards and forwards, doing that. The electrons are moving in the way shown there. Okay, let's do a very similar one. So what happened? This is happening in water. So whenever you have water, H2O, it reacts with another water molecule, and one water gives away a proton and 1 accepts the proton. So the black one is going to become H3O plus, that's gained the proton, and the red one has lost a proton, that becomes OH minus. And this equilibrium is happening all the time whenever you have water, but it's very far to the left. Okay, so the equilibrium is far to the left. In fact, it's about 1 in 10 million water molecules that actually does this reaction. Most of it is just as H2O, a very small proportion of these two. Okay, but let's draw that as a curly arrow reaction mechanism then. So what we got, H2O, black got a black H2O, and we've got our red H2O. And right, I'm going to put, there are really 2 lone pairs on that oxygen, aren't there? But I'm going to draw 1. And what's that got to do is that, well, the pair of electrons is, I should probably do this a blue arrow this time because I've used up red. That pair of electrons in the lone pair is going to stretch forward and form a bonding pair to that hydrogen. This hydrogen will now be forming, can't form 2 bonds, so simultaneously as that happens, this bonding pair has got to shrink back and form a lone pair on the oxygen. So if we've got that there, we would have, right, this water has now got an extra H, right, really the positive charge on the whole thing, but quite often you'll see that people just draw it on the oxygen, so I'll do that same, draw in brackets, positive charge on the oxygen there, and put a circle around it so it doesn't just look, just so it doesn't look like a bit of ink on the page. And the red water has become OH minus. Okay, now let's see, if we do that backwards, what's going to happen? Well, I need to put a lone pair on that oxygen. There's really 3, I'm only going to draw 1, and that's going to stretch out and form a bonding pair to the hydrogen, and again this bonding pair is going to shrink back and form a lone pair, so that's going to go like that. So that would be how you would show that reaction occurring with curly arrows. Right, let's have a look at one which is probably, let's think about carboxylic acids. Okay, well, we've come across carboxylic acids GCSE, and right, here's a carboxylic acid. Right, now what they tend to do is they tend to lose this hydrogen. Okay, and so if I draw, they lose that hydrogen, it comes off as H plus. So what I need to do is, right, that comes off as H plus, so that pair of electrons there, the bonding pair is, well, hydrogen has contributed an electron to that, but it's going to lose it. Okay, it's going to go onto the oxygen. So what we're going to draw there, well, we've obviously got this hydrogen as H plus, and now we need to be careful thinking what we've got left over here. Right, is that right? It's not quite right, because look, there's a pair of electrons in that bond there. It draws a dot and a cross. 1 came from the oxygen, 1 came from the hydrogen. The hydrogen has left its behind, hasn't it? So this oxygen here would have a negative charge on it. So that's what would be happening there. Okay, and a hydrogen H plus sign. As you notice, charge is conserved. So on this side of the equation, yeah, 0, that's neutral, that's negative, and that's positive. So that altogether, that makes it neutral, doesn't it? Now, also, really, what I've done there is, this is not quite telling the full story, because when you put a, you can't have an H plus ion just floating around by itself. So really, what's happening there is going to be a bit more picky about it. What you should, and you should actually write that like this. You should write down CH3, C double bond O, OH. That's going to go to a water molecule. So I'm going to draw a water molecule in here. Right, this bit is absolutely, I'm going to draw that in blue because I don't want to use all, saves a red arrow, yeah. So showing electrons. There's our water molecule. So what's going to happen, right, that bond breaks, yeah, that bit's right. So it goes back to being a lone pair. But this hydrogen can't just float off as an H plus ion. it's really H3O plus, isn't it? So what happens there is, right, let's draw a lone pair on this oxygen, stretches out and forms a bonding pair to that hydrogen. So yeah, we form the negative ion. That was, but really, rather than just the H plus ion, which is shorthand really, what we've got is got H3O. So there's the water with the hydrogen piggybacked on it, that forming a dated bond that has come from the ethanoic acid. So now this is correct. Yeah, this is a bit of a shortcut, but it's completely okay in exams. Okay, so we don't normally show the H plus being picked up by the water, whatever. It's fine to just show it coming off as H plus, but it's understood that's not really the case. Right, I think we've got time for one more. Okay, right, let's have a haloalkane here. I'm going to draw. Right, so I'm going to have a CH3 there, a CH3 there, and a CH3 there, and I'm going to have a bromine there. Now, what can happen sometimes, and we don't really, it's not really on our specification, but it can happen, is sometimes without anything happening, the pair of electrons in this bond here, they can just both shrink back and form a lone pair on the bromine. Now, what would we have if that was the case? So don't forget, there's a pair of electrons in that bond there. One came from the bromine, one came from the carbon. Who's got them both now? Bromine. So the bromine's got one electron it shouldn't really have, so that's Br minus. So what's left over then? We're going to have CH3. Nothing happens to all that. That stays exactly the same. But the bromine's gone. But what we should have there is, can you see, there should be a positive charge on that carbon. Right, that's a positively charged carbon because the electron that it gave in the bond, in the haloalkane, has now been taken by the bromine, Br minus. Again, this principle of conservation of charge is quite useful. That side of the equation, 0, we've got a minus there, and so we must have a positive there in order to make the overall charge 0. Okay, so that's just a few more examples of how we can use, get you a little bit more familiar with using curly arrows.